ABG interpretation starts with just one question. Is the patient acidotic or alkalotic? Before looking at bicarbonate or carbon dioxide, always read the pH. A pH below 7.35 indicates acidemia, while a pH above 7.45 indicates alkalemia. Blood pH is determined by two variables: arterial carbon dioxide, which is regulated by the lungs, and bicarbonate, which is regulated by the kidneys. If the primary problem is an increase or decrease in the arterial carbon dioxide, it's a respiratory disorder. If the primary abnormality is in bicarbonate, it's a metabolic disorder. Here's the trick. Opposite direction, think respiratory. Same direction, think metabolic. In respiratory disorders, the pH and arterial carbon dioxide move in opposite directions. If the arterial carbon dioxide increases, the pH falls. That's respiratory acidosis. If arterial carbon dioxide decreases, pH rises. That's respiratory alkalosis. In metabolic disorders, pH and bicarbonate move in the same direction. If bicarbonate decreases, pH decreases, that's metabolic acidosis. If bicarbonate increases, pH increases, that's metabolic alkalosis. Once you've identified the primary disorder, the next step is to check whether the body is compensating appropriately. Apply this algorithm to all the conditions beginning with metabolic acidosis. So once we've identified low bicarbonate as the primary disorder, we need to check whether the lungs are compensating appropriately. So for that, we use the Winter's formula to calculate the expected arterial carbon dioxide using the formula 1.5 times bicarbonate plus 8 with an error of 2. Now, if your measured arterial carbon dioxide is within the expected range, the respiratory compensation is appropriate. If it is higher than expected, the patient also has some respiratory acidosis. If it is lower than expected, then there is an additional respiratory alkalosis. Only after checking the compensation should you check the anion gap. If the anion gap is normal, the delta ratio is not required, and it indicates that there is hyperchloremic metabolic acidosis. It rules out addition of abnormal acids like lactic acids and salicylates. Now, if the anion gap is elevated, we know it is HAGMA or high anion gap metabolic acidosis, and that's when we calculate our delta ratio. Delta ratio is the change in anion gap from normal to change in bicarbonate from normal. So the formula goes anion gap minus 12 is to 24 minus bicarbonate. Now there's a whole scale here. If it is less than 0.4, it is NAGMA. If it is between 0.4 to 0.8, it's a mixed NAGMA and HAGMA disorder. If it is between 0.8 to 2, we have a pure HAGMA. And if it is greater than 2, then we have HAGMA. And in addition to HAGMA, we have metabolic alkalosis or respiratory acidosis. So remember the sequence for all 4 disorders. We'll first look at the compensation, then the anion gap, and lastly the delta ratio. Now let's move on to metabolic alkalosis. Here the primary abnormality is an increase in bicarbonate. To compensate, the lungs hypoventilate, retaining carbon dioxide. As the carbon dioxide rises, the pH moves back to normal. Now to check whether this compensation is appropriate, we calculate it using the formula 0.7 times bicarbonate plus 20 with an error of 5. Now once again, if it falls within the measured range, respiratory compensation is appropriate. If it is higher than expected, then we think of additional respiratory acidosis. If lower than expected, we suspect a concurrent respiratory alkalosis. Remember, compensation never overcorrects pH. It only moves it closer to the normal. Now let's look at respiratory alkalosis. Here the primary problem is a decrease in arterial carbon dioxide, usually due to hyperventilation. So the kidneys compensate by excreting bicarbonate. So the bicarbonate levels fall. So the amount of compensation will depend whether the disorder is acute or chronic. In acute respiratory alkalosis, the kidneys haven't had enough time to respond, so bicarbonate will decrease by about 2 milliequivalents per liter for every 10 Hg fall in arterial carbon dioxide. In chronic respiratory alkalosis, the kidneys have fully adapted, so the bicarbonate decreases by 5 milliequivalent per liter for every 10 Hg fall of arterial carbon dioxide. If the measured bicarbonate doesn't match these expected values, then we think of an additional metabolic acid-base disorder rather than simple compensation. Just remember, acute changes are small, chronic changes are larger because the kidneys have had time to compensate. Lastly, let's look at respiratory acidosis. Here, the primary abnormality is an increase in arterial carbon dioxide, usually due to hypoventilation. The kidneys again compensate by retaining bicarbonate, so bicarbonate levels will rise. Now, once again, the compensation will depend on whether the disorder is acute or chronic. In acute respiratory acidosis, the bicarbonate will increase by 1 milliequivalent per liter for every 10 Hg rise. And in chronic respiratory acidosis, the kidneys have had time to adapt, so the bicarbonate increases by 4 milliequivalent per liter for every 10 Hg rise of arterial carbon dioxide. Now, there's an easy way to remember all four respiratory compensation rule. I call it the 1-2-4-5 rule. For acidosis, remember 1-4. For alkalosis, remember 2-5. Remember, acute changes are smaller, chronic changes are larger. Now it's your turn. On the next slide, I have got a mixed acid-base disorder question. Don't guess. Follow the exact algorithm we discussed. Read the pH, identify the primary disorder, check compensation, calculate anion gap, and use the delta ratio if needed. Pause the video and solve the question and see the answer in the comments. And if this video has helped make ABG feel a little less scary, please hit like, share, and subscribe. I'll see you soon with my MCQ challenge. Happy understanding.